Hello and welcome to DevSecOn Australia. We are a chapter of the global DevSecOn community, an inclusive community that educates and enables developers in application security. Coming up, we'll be joined by the one and only Adam Furmanek, DevRel at Metis, talking about database guardrails, which is a topic about the new age for developers and databases. So seems interesting, and I'm very excited to hear that's going to be about. But before we dive into that, I want to quickly introduce myself. My name is Diran Tal. I'm a developer advocate here at Sneak, doing a lot of developer relation stuff. I'm not usually the host. Were able to see here, but unfortunately, we had our awesome chapter leader having to step down from DevSecOn Australia. So if you have to, want to share, the hosting session and just want to join in, please, getting involved is super fun and inclusive, and there's a really cool community here. So this is going to be fantastic, and I'm going to be very happy to hear about it. So if you do, head over to devsecon.com, which is the website, has all the details on how to join. Shoot us an email to info@devsecon.com. We'd love to have you on board. We'd also love to have your feedback so we can improve. So anything you can share with us either on Twitter or on the Discord server for DevSecOn, which is also on the website. That's a really great place to just leave any feedback and interact with our community. It's actually where all of our fellow speakers are there and the rest of the members of the DevSecOn community. So please sign up on the devsecon.com website. And we'll be happy to just have you on the Discord server for any questions you want to ask Adam on this session or just generally to the community itself. Once the session is over, you will be able to rewatch it on the website, share it with friends, colleagues, or both. DevSecOn is brought to you by Sneak. Our aim is to create a vendor-neutral place to share knowledge and best practices for related to software security. So right now, that's all of my information to give you. And without further ado, I'm going to bring in Adam. So Adam, let's bring you in.
Hello, everyone. Thank you for tuning in.
Yeah, for sure. How's it going? This is the afternoon there in Australia.
Oh, yeah, afternoon in Australia, but I'm in Poland, Europe, so it's like early morning for me, 10 a.m.
All right, so we're both still waking up, I guess, the morning coffee.
Yeah, exactly right, first cup.
All right, cool. So I'll let you introduce yourself and get started with the slides, and I'll be just right here moderating any questions, anything that comes up.
Oh, cool. Thank you. So hello, everyone, and thank you for tuning in once again. My name is Adam Furmanek, and as already mentioned, I'm DevRel at Metis. And today we are going to talk about database guardrails. So during the next 1 hour, we are going to see what that concept is and why it's even worth exploring. I used to be a software engineer for many years, doing front and back and machine learning databases, other various stuff. And generally over the years, I learned about various hardships, various pitfalls that we as developers fall into. And this talk about database guardrails is specifically designed, to show you and to discuss a couple of those issues, especially around the domain of databases. We are going to see how the world has evolved over the last decade, how the things has changed, where we used to be 15 years ago, and where we are now. And with all that comes great challenges that we need to solve nowadays. So this is the idea. This is what we need to do. So let's now move on to the slides and let's just jump straight to it. So many years back, like 15 years ago, which is basically long ages in the computer science, we used to be in a world where we generally had everything under our control. Things were rather straightforward, meaning that our applications were generally relatively small. We had something like, a SQL database, we had a couple of nodes if we decided to scale out our application, and we had user that was basically hitting the load balancer and, getting the requests and whatnot. So this is generally how it used to be. When we wanted to deploy a new application, this new application was generally completely independent from the previous one. Our ecosystem was very predictable. And if there was something wrong with our applications, it was much easier for us to pinpoint where the reason, where the issue was. We could just examine the logs, we could attach the remote debugger, and bang, we had all the answers, what was going wrong and how to fix the issues, obviously after some bit of troubleshooting, but generally pinpointing the exact point and where things were going wrong was rather straightforward. But that was like years back. Now the world has changed significantly. When we take a look at the landscape of our applications today, things are much different. First, we do not have like one application anymore. When we take a look at how it goes, we can see like multiple things playing together and interconnected with each other, talking to each other constantly to deliver the ultimate performance. Second, we learned about different practices for the deployment and for the organization of our code, right? We have microservices, we have domain-driven design, we have serverless, we have AWS Lambda, Azure Functions, and other stuff that allows us to basically cut the big picture into smaller pieces that we can deploy and develop independently. Meaning that now we don't need to deploy one big monolithical application. What we can do instead is we can deploy just a very tiny piece of the code, which is running in like Lambda or some container or Docker, Kubernetes, and other stuff, and we can scale out these things independently. Similarly, when it comes to organizing our domain, our databases, our data storage, first, we have many more solutions. Previously, it was generally SQL database, right? But now it's SQL database, NoSQL database of various kind. We have various like mixes of SQL with NoSQL. We can take Postgres instance and add like PG vector and have like vector database in that. We have JSON-B supported directly natively by PostgreSQL, right? So we have like this mix of various different technologies working together and delivering this different experience. Another thing that we need to consider here is how things evolve from the terms of maintenance. Previously, when something was wrong, we could just, read the logs of our monolithical application and we saw where the reason, what the issue is, right? Now, finding the logs is much harder. We have logs from our application, security logs like network logs. We have logs from our queuing mechanism, enterprise service bus, notification service, database of various kinds, serverless deployment, whatever else. Just finding the proper log is now non-trivial, not to mention the intercommunication between the things in the system. Finding one log is not enough anymore. We need to find logs across the landscape to understand what is going wrong and where the issue is. And specifically, when talking about databases, managing, maintaining, and tuning databases is now harder than ever. Previously, we could just go with, one DBA in our team that was maintaining a couple of SQL databases. When performance was going down, we could easily figure out how to deal with that. Add indexes, reorganize the database. We knew how things work and we had them under our control. Now, things are getting way harder. One DBA won't manage to deal with all of that. Developers are changing the databases with infrastructure as code. We have multiple databases running in together, multiple different technologies for storing the data, different ways of organizing the databases. Domain-driven design makes it even harder because we cut the domain into like bounded context, and each bounded context need to basically replicate the data between. So just seeing why the performance goes down is much harder. Not to mention how to figure out what's the reason. It's not only about, talking that, hey, your CPU spiked, but understanding why it has happened. Maybe there was a scheduled task behind the scenes. Maybe there was a bug. Maybe we stopped using an index. Now optimizing databases is generally non-trivial. And things can get even worse when we start talking about multi-tenancy. Previously, when we were just implementing application and we didn't need to deal with multi-tenancy that much, we didn't need to consider, okay, how to figure out which of our clients is actually causing the issue, right? things now are getting worse, because with multi-tenancy, we have first multiple approaches how to do that. Maybe we should have one database with like tenant ID. Maybe we should have multiple databases independently for each tenant, depending whether the tenant is just a regular business client, or maybe it's a government facility, or maybe it's some other organization that handles critical data, and we just can't avoid like putting their database independently in some another data center just to increase the security. But if we do that, then we have even more databases to observe, monitor, and tune afterwards. So multi-tenancy makes these things even harder. And the important part to understand here is that it's not something that applies only to big corps. It's something that is the same way applicable to small startups, to regular applications, to big applications powering like government or big corp or Fortune 500 or other stuff. This is basically the reality we're in today. And we just can't avoid that. It's a must for us to live with this reality and be able to deal with that. Even when we take a look at like seemingly regular design of, some system, it's like a design I took from Google, just typed architecture design, and bang, there you go. How many components there are in this thing? How many different things working together? Storage, blob storage, SQS, notification service, identity provider, security provider, some load balancers, yada, yada. And this is just for one application. And now we have multiple applications like that, one deployed many times every single day and talking to each other. So how can we reason about these things? Well, the thing is, there is no straightforward way. We learned already that just examining logs is not enough for us. We need to have something like, okay, let's take monitoring to the play. Let's get some metrics, let's get some signals. But when we open up like monitoring dashboards, this is typically what we get. We have tons of signals showing the health state of our application, showing whether application is green or not. But if it's red, if something is burning, we do not have any insight into what is actually the reason. We get the information, hey, things are going wrong, but we don't know whether it's because the hardware is faulty, the deployment got stuck, the scheduled task got delayed, or maybe we're running in different like data distribution nowadays. So this is the reality we need to deal with. And the way to fix that is something that we need to take on. We as developers, we need to finally own the databases to make sure that we can prevent the bad code from reaching production. We can monitor our systems, and finally we can troubleshoot them efficiently. So this is something we need to do, and this is where database guardrails come into play. Database guardrails are supposed to protect us from things that break every day. But in order to understand how they can help us, we need to understand what goes wrong. So let's discuss a couple of things that may break and that actually breaks every single day, and see how our current solutions for monitoring, for testing, for maintenance and deployment, how can they deal with what we observe daily. So when we talk about databases, generally all the issues with databases can be grouped in like 3 different big groups, presenting like, or grouping them, explaining what's going on. The first thing is, well, code changes. We introduce code changes every single day. We do deployments more often than never. People tell us we need to deploy anytime during the week, on Friday afternoon, anytime during the day, generally commit and push to production, right? This is what we should have with continuous deployment. And code changes may break our solution, obviously. We change the code, we start getting different data, accessing different columns, using different tables, and the performance degrades, the solutions break, we have issues, we have performance degradation. That's one thing. The other thing is about schema changes. We introduce schema changes, schema migrations daily, right? We add new columns, we add new tables. And when we do something like this, it's always risky, because when we change the column type, we may degrade the performance as well. We'll look into that a little bit later, but just to give you understanding of what's going on, just by changing the column type, we may in fact change how the query is executed, how the execution plan changes, and effectively we may break the applications. It's even more important nowadays when multiple applications talk to the same database and we have these heterogeneous applications talking to the same data storage. One application is being written like in JavaScript, the other is in .NET, yet another is written in Go. All of them, they talk to the same database, and now when we change, for instance, the column type, ORM libraries in different technologies may simply break. But yet another big category of problems is the query change. The query change not in a sense that, hey, we changed the code of the query, but in a sense that the query began to execute differently. Meaning that previously it was using an index, now it's not. Previously it was using this different join strategy, now it's using another one. Previously it was using some optimization hints, now it stopped doing so. And these things can change even if we do not change the application per se. They can change because we have like different data distribution pattern, we deploy application to different region, or we change the database configuration behind the scenes. So those three different categories about databases, they generally tell us what can go wrong. We can break the code, we can break the database, or we can change something that still makes our queries work, return the same data, but they are now working way slower and just can't cope with the performance anymore. There are other issues behind the scenes, like about missing indexes, data quality, locking, configuration, transaction isolation, caching, pooling, yada yada, other things that can fall into these categories. But generally, let's now see about like examples from each of these categories to understand what we are dealing with and how our today's solutions can deal with them. So the very first thing is, let's take slow queries. So imagine that we have basically an application code like this one. So we take the user aggregate root and we would like to get the user with this given ID and get some more details for this particular user, like pages, text, questions, whatever. This is actually the example I once faced in my production code. So the application code on the left resulted in the SQL statement that you can see here on the right, which has something like, I don't know, 8 different joins in here. And this query was executing for nearly 25 seconds and extracting 300,000 rows from the database. Most of the time that the application spent in here was not on extracting the data from database, but on processing all those duplicates that were extracted from the database, because this query leads to exponential increase in the number of rows, right? Just because we have this many joins in the query. And now the question is, how can we fix such an issue and how can we avoid even such an issue? The problem with finding that issue is, hey, the unit tests will not find the problem here, because we have unit tests, we have integration tests, but they focus on the result of the query, of what data we get from the database. They do not focus on the performance of the database. And even if you try that like manually on your local environment, then most likely you have 10 different rows in your database. You probably cleaned up the database for your unit tests. So this query is blazingly fast when you run it locally. The problem emerges when you deploy that to production and when things are actually running with, millions of rows you have in your database, and then such a simple query may extract 300,000 rows and lead to problems. How can you fix that? At least in that case, the solution was rather straightforward. Instead of getting everything in one go, just get multiple pieces of the aggregate root, of the user root, and then merge all of them together in the application code. This leads to many more SQL queries being executed, right? So we have multiple different queries being executed, which may seem like, okay, that's not necessarily a good idea, but because those queries run much faster, then ultimately this whole experience is like way smoother and all things go faster, just because we extract much fewer rows together. Again, unit tests will not see any difference between those two cases, right? Because unit tests and integration tests, they focus on the correctness of the data, not on the performance behind the scenes. Another thing we may see is, let's say that we want to increase the readability of our code. Let's take the common table expression with such a table. We have boarding passes that has something like 8 million rows. And what we want to do, this is a handcrafted example showing you the problem. And the query we want to send is, let's take like all the rows from boarding passes, and then for each like ticket number, for each boarding pass ticket number, we want to calculate the checksum twice and store it with CTE. And CTE, if you don't know what it is, it's kind of like a named temporary table for this given query. So then we take this temporary table called CTE performance and we join it together like 3 times based on the ticket number, flight ID, and boarding number, and we look for rows with given like double checksum of the ticket number. However, this query with CTE is equivalent to the query we see here at the bottom, which joins the boarding passes 3 times and then calculates the double checksum of the ticket number directly inside the where filter instead of, creating this temporary table. And those 2 queries are again equivalent. They return exactly the same data, and in theory, they should be, like when it comes to the performance, they should be of the same, execute with the same time. The latency of the query should be the same. Unfortunately, the common table expression executes in 13 seconds, whereas the less readable query with lots of repetition executes in 8 seconds. There's nearly a double, like twice as long as this less readable query. So just by changing the readability of our queries, just by changing how we structure the query, we may change the performance significantly. Once again, unit tests, integration tests won't capture that. Why? Because they focus on correctness, not on the performance. Yet another thing we can discuss is schema changes, right? Adding a column may also decrease the performance if we go with select star statements. Select star statements will extract all the columns that we have in the table. So if we add a new column, then we start getting more and more data, which may lead to worse performance. Also, adding a column may cause table reorganization, basically table rewrite, meaning that once we try adding such a column, the database engine needs to take all the data on the side, drop the table, create new table with new schema, and then copy the data back to the table, right? And this is something, this table rewrite may take minutes or even hours and leads to basically database outage. Our system is down because the table is blocked. So we can't move forward and we need to wait until this schema migration finishes. The problem with schema migration and testing and all the stuff we have in our continuous integration pipelines is that all the tests, unit tests, integration tests, they execute against the latest schema. They do not check how long it takes to migrate the table from one schema to another, because those things are not even part of the test. Not to mention that when we run such a schema migration locally, then the performance is obviously blazingly fast just because we have, 10 rows in our local database. So generally, table migration is much faster than when we run things in production. Another thing is dropping a column or changing the column type. This thing is always tricky and always dangerous because we have heterogeneous applications nowadays. We have one application written in .NET, yet another application written in JavaScript. And when we update the schema, table schema, then what happens is we focus on one particular application that we now want to run with our test suite. When we run unit tests, we run against the new database schema, and we do not consider that, hey, maybe something has changed the schema for us. So when we run this migration, some other application may break just because it hasn't been migrated to the latest schema yet. And those things are much harder to be captured in unit tests, integration tests, or generally in test suite, just because, we do not consider problems like that, and we don't see those interconnected pieces together. When it comes to changing the schema type, now by doing that, we may first decrease the performance because we change the internal representation of the data. We may break the data quality, for instance, by changing, I don't know, numerical precision of some column. We may break the application because ORM cannot cope with the new representation of data anymore. Think about, I don't know, spatial data, geo-coordinates, or other stuff that some ORMs can't even handle properly. And this may also cause table reorganization, table rewrite again, which may kill the performance and take the database down for minutes or even hours. Again, something that we do not see when we implement our application, something we learn about when we go to production. Yet another thing about performance is, hey, missing indexes, right? When our queries are slow, then it means typically that, hey, we use table scan instead of index scan, or maybe our queries use functions that we can't pre-calculate efficiently or whatever else. What do we typically do? Well, we need to add indexes, right? But when it comes to indexing, there are multiple ways, multiple different types of indexes, right? Indexes for regular data, for JSON data, for vector data. How do we know which index to use? But more importantly, how do we know whether index is being used properly when we test our applications locally or where we run them through the pipelines? Again, unit tests do not capture that at all because they only focus on the correctness. But even worse case is when we tell a junior developer that, hey, when your database is slow, just add an index. What happens next is, bang, we have indexes everywhere. And while those indexes, they do improve the query performance when it comes to reading the data, they negatively impact the performance when we add the data to the database. They break the performance of insertion, deletion, updates, other stuff. Again, something we won't even notice, because when we focus as developers, when we focus on improving the read performance, and even if we measure the read performance, then by adding an index, we may accidentally break something else like addition, which we don't measure just because, hey, now we focus on reading the data, right? So generally, those are the things with indexes that first, they are very hard to notice, but more importantly, we don't even know when the indexes change behind the scenes. We can test indexes locally, but how do we know whether the index is actually being used in production? Or maybe it has been used for 6 months, but now something else has changed and the index isn't useful anymore. Do we get any signal about that? Do we get any monitoring? Do we get any alert that, hey, this index is now decreasing performance and not helping at all? Those are the things that we have about databases, but there are many more issues around them. For instance, bugs. It sounds easy enough that, hey, there are some bugs that we can capture with unit tests. For instance, if we forget to add where condition to delete statement, yes, we'll capture that bug with unit tests. But what about issues in the databases themselves? If you didn't know about how databases need to deal with concurrency, with multiple transactions running together, I highly recommend you take a look at the Jepsen project, which shows how distributed databases can lose the data. For instance, Mongo was well known for many years that under heavy load, it was losing the data because databases have bugs. One of the worth mentioning bug is called Halloween problem. This is a very old problem, and now our databases protect themselves from being prone to that. What happened is probably something like, I think it was 40 years back around that time, on a Halloween, one company decided to give a pay rise to all the employees. So what they wanted to do is they wanted to basically run this query on the database. So let's take all the employees, and for every employee that earns less than some value like 10,000 here, let's increase their salary by 10%. Okay? Simple enough. But because how databases organize the data behind the scenes, the problem was that the rows were ordered and put in order based on the salary. So you take a first row, you check, is the salary below 10,000? It is, so I increase that by 10%. And then what happens? physically this row was changing place on the storage drive and moving somewhere else. So then the database was iterating over other rows to finally find the same row again. Is the salary below 10,000? Still is. So let's increase it by 10% again. And the problem was on Halloween day, that company effectively gave the pay rise to all the employees so that everyone who was earning less than 10,000 started earning at least 10,000 and more. Right? So this was the problem. And this is a bug in the database itself. And there are so many other bugs that are hard to notice, hard to find, and even harder to debug. So I highly recommend Jepsen project again. But generally, those things can break. And how do we figure out there is something wrong? Our unit tests will not capture these issues because, well, we don't overload our system. We don't see what's going on under heavy load when we have like lack of resources, lack of CPU, and whatnot. But moving on, there are other issues introduced by ORMs as well. So the libraries we use to interoperate with the database. One of the well-known issues, and I guess you know that, is something like n+1 selects problem. So let's say that we have aircraft table that is connected or in relationship with seats table in one-to-many relationship. So one aircraft can have multiple seats. And what we want to do is we want to take this simple application code, get all the aircrafts, and then for each aircraft, we would like to see how many seats it has, right? So this query, this application code may generate multiple queries, SQL queries behind the scenes. One query to get all the aircrafts, and then for every single aircraft, let's get all the seats with yet another query. So it turns that it generates n+1 queries, one for aircrafts and n additional queries for each particular aircraft. How can we fix that? Well, we can fix that by changing our ORM into so-called eager mode. And eager mode means that an entity is extracted with all the dependencies from the databases just by using one single query, which uses left join in here. So this is how we need to change the application. But the important part here is, first, we don't notice that with unit tests because, again, we always get the same result, only the performance is different. And second, we don't even see how it's working just by looking at the application code. The configuration of your ORM is something that is typically very far away from the application code, right? So you don't know whether you have lazy loading here or eager loading. And another case is you can't just change your ORM to always go with eager mode, because then you end up with the issue we already saw. Then you end up with the case that, hey, you join so many tables together and you extract so much of the data, then it kills your performance, basically. So generally, there is no silver bullet, no one solution that fits all. We need to examine these queries one by one to see what brings the best performance. Another thing that we have with ORMs is how to put our object-oriented data into the SQL database, which is a completely different paradigm. Object-oriented world is incompatible with the SQL world, and this is what we call impedance mismatch. These two, object-oriented and SQL, have completely different characteristics. So when we start putting one model on the other one, then we may run into performance issues. For instance, there are some patterns how to structure like inheritance in the SQL world. And those patterns are like table per hierarchy, table per type, and yada, yada. But even though they will work technically and bring us the correct data, they may decrease the performance. Again, something we won't capture at all. Other issues with ORMs are, for instance, around like the data types. If you change your string type, you may get different performance. However, our object-oriented languages, or generally most programming languages, don't let us change how the strings behave. For instance, in SQL world, you have something that is called collation, which is basically an order of characters in the alphabet and the rules how to compare characters, whether like lowercase letter is equal to uppercase letter and whatnot. So now when you change collation in your SQL database, then you change the equality comparison operator. right? But this is not something that you have in your application code. In your Java language, you can't change how you compare your strings just like that, how you overload the equals operator, right? Okay, you can change that by calling different methods, by providing parameters, but this is something that can be changed in the database, and you won't notice that in your application code. So those are the things that break when it comes to interoperating between object-oriented world or generally programming world and the databases. But moving on, there are other issues that ORMs hide from us, like transaction isolation level. What is the default level we use? Is it serializable or is it read committed? Do you know that on read committed, which is used by default in most cases, you can get duplicates in your database, meaning that when you read select star from table, you may get the same row returned twice. Or maybe you can miss a row that was in this database. What is the transaction scope? Who begins the transaction? Who closes the transaction? Who decides where the rollback happens and whether everything goes rolled back or just the nested transaction? What about caching, connection pooling, query hints? What about eager lazy configuration? What about using stored procedures and other stuff? Generally, ORMs hide so much from us that it's much harder to reason what's going on behind the scenes. When it comes to migrations, there is yet another case about ORMs. Is your ORM in charge of migrating your table schema? Is it some separate tool? When does the migration run? Can your ORM deal with the schema drift? So when your ORM detects that the table doesn't look like the ORM expected, is the ORM going to fix that? Or maybe it will throw an error. Who decides what's going to happen? How do you deal with like rolling things back when it comes to schema migrations? How do you fix issues around that and whatnot? Many other things that we need to deal with when talking about ORMs. So things are getting harder and harder over the way because ORMs and because generally all the libraries that we use, they scatter configuration in various places and they hide all of that behind the scenes and we have no idea what's going on. So now we can finally ask the question, okay, we know all these problems, they can happen. Do we capture them before going to production? Do we, as DevOps, as software engineers, with CI/CD pipelines, with continuous deployments happening daily, do we capture these errors before going to production? And when we take unit tests, the answer is nope, we don't capture those. Why? Because unit tests, they focus on correctness of the data. They will capture some like incorrect queries, but they will never capture n+1 problems unless you specifically implement a test that checks whether you have n+1 problem. They won't capture like performance issues. And what's worse, they won't figure out that something doesn't work or won't work in production. Because you may have your index configured properly in local environment, but the same index may not exist in production or may be ignored by your database. And unit tests won't capture that at all. Integration tests, same story here. You won't capture things just because integration tests focus on different part. End-to-end tests, some issues you may capture using E2E tests, right? But only if you have enough data in your database and you know what to look for and you have all of that automated. But generally, those issues that we just discussed, they will go unnoticed and we'll deploy them to production and will break the production environment. There is another approach, though, we could consider here, which is load testing. Okay, maybe we can load test our application before deploying to production to see whether the performance is okay. And generally, it works. This is the approach that works. But there are so many problems with them, which makes load testing basically something we shouldn't rely on that much. First problem is cost. You need to run load tests for hours to get the proper performance because we need to think about caching, about tier compilation, about interoperation between systems and whatnot. So this takes time. This takes money. You need to create another fleet where you start hitting the load test, right? So those other machines, they basically cost, so you need to pay for them. Not to mention if you have solutions that use, I don't know, GPU instances for machine learning, right? Getting GPU instances is crazy expensive nowadays, so generally load tests are not cheap, unfortunately. Another thing is about how to do load tests properly. What about data distribution? Do you get correct data? Do you need to anonymize the data? Do you need to anonymize social security numbers? Can you take data from production? What about the data from the US or from Europe? Can you like interchange them? Or maybe the data patterns, different countries, they change the data access patterns, which makes your load tests not necessarily showing the actual problems. What if the problem is in some tiny country, right? So that you don't see the metrics degradation when you run load tests, just because the number of requests coming from, I don't know, Luxembourg is so small that they do not manifest themselves in the overall metrics. But still, every person in Luxembourg will basically find your application unusable just because your performance spiked. What about other stuff around, even replying the traffic properly? What if your application is stateful? Can you just take the queries from the production and run them the same way against your staging environment? You probably cannot, just because you have a state that should be preserved between all those executions, right? So those things is something that we generally can't do properly. But there is one more problem with load testing. The problem which is the worst and which makes load tests, unfortunately, not very helpful in what we discuss in modern, fast-paced world. The problem with load tests is they happen at the very end of the pipeline. So even though we wrote our application, we are done with the design, with code changes, we did unit tests, we did code reviews, we learn after probably even days that something is wrong. And this is way too late to efficiently fix the issues. We should get the info that, hey, something is going to break in production. We should get that information right at the very moment when we type the code. And load tests won't give that to us. And unfortunately, they are not working well in this sense. So how can we do better? How can we fix all those problems that I just mentioned? The solution we want to propose is database guardrails. Database guardrails is a solution to prevent the bad code from reaching production, to provide monitoring and observability to your solutions that focus on the actual issues, not on the metrics. And finally, they let you automatically troubleshoot the problems we have. In order to build database guardrails, we need to be able to understand what's going on in our ecosystem. We need to have the context to find all the root causes and to provide all the solutions. And we are now going to see how to build these database guardrails. So generally, database guardrails, they focus on bringing all pieces together to make sure that the problem can be identified as early as possible. And even if it goes to production, then we can troubleshoot it efficiently and give an answer what exactly is not working. Not in a sense that, hey, your CPU is 100%. No, but instead you deployed this change, it uses different data access pattern, your index isn't used anymore, and that's why your performance drops. And in order to build that, we need to understand that first step is always telemetry. Telemetry is this ability to collect data from various places. Ability, so we have tools and we have standards and libraries to do that. For instance, OpenTelemetry. Once we have that in all the places, in our SQL database, application code, load balancers, queuing mechanism, enterprise service bus, yada, yada, we can finally build the visibility. Visibility shows what's in the system. We can see things on our dashboards and we can finally see what's going on. But then we can build the thing which is called APM, Application Performance Management, which is basically showing the end-to-end health state of the system, showing all is green, or maybe there is a fire in this place that spreads around. But APM is not enough. APM will tell you, hey, there is a problem over there, but you don't know what's the source of this problem. And it's observability that lets you connect all the dots and bring you all the answers to the questions you may have, showing you the problem is caused because of that, and this is how we fix that. And the difference between monitoring and observability is monitoring focuses on errors, on metrics, on charts, on graphs that are super useful for like DB administrators or generalists administrators, but they are not super useful for developers because they give you only raw signals that you don't know how to tackle, how to action. And observability gives you something better, tells you the story and how to deal with the story. This is observability. And in order to finally bring database guardrails to developers and let developers own their databases, just like they own their pipelines, just like they own their infrastructure, we need to have the database guardrails. They can tell you and give you actionable insights. So in order to do that, we need to first start with OpenTelemetry. OpenTelemetry gives us logs, traces, metrics. So basically ability to capture what's happening, to see what inside our applications. OpenTelemetry is basically a set of SDKs for various languages that allow us to capture signals, being traces, metrics, capture them together and correlate them with each other. So the way it works is when we have OpenTelemetry and we have multiple applications going on together, we can see that, hey, for instance, there is a workflow like checkout workflow. So the user called our load balancer, which then calls, I don't know, the application server, which then goes to a database, which then goes to some storage like blob storage, which then goes to mailing server and whatnot. So this is basically how the workflow propagates throughout our system. And OpenTelemetry allows us and helps us to turn these interactions into a thing that we call trace. And trace is basically this diagram showing us what was going on, and each part of each system happening or participating in this workflow is presented here as a separate rectangle, and those rectangles are called spans. And each span carries some information, like the timestamps of what happened, the IDs of what was going on, or maybe the human readable name or information of what was happening with some attributes happening or going on behind the scenes. So with OpenTelemetry, we can extract these signals and be able to reason about them. Now, the way we would like to use them is we need to use them to build the observability around the databases. So what we can do is we can understand how things work behind the scenes. And whenever we send a query to database like select star from table, it goes through various stages. For instance, it goes through parsing. So the database engine parses it into some computer readable representation, which is called abstract syntax tree. Then it's rewritten to apply some optimizations, to apply some things like removing aliases or making sure that all aliases put to the same point and other stuff. And finally, the database engine plans how to execute the query. The planning part is the most important one because it can tell us how fast the query is going to be executed. So if we ask our database, for instance, Postgres, I can ask how it's going to execute the query by using this explain keyword. It can give me this query plan showing exactly what is going on and what will be executed by the database engine. And when we dissect this execution plan, we can see that it consists of multiple nodes, each node representing some operation. For instance, this can be like table scan, index scan, sorting the rows, filtering the rows, yada, yada. It can mention which indexes it uses, what strategies it uses to join tables and whatnot. But most importantly, it tells us what's the anticipated cost of the operation. And this cost is some arbitrary number. It is not something meaning that, I don't know, 6 units of CPU or 6 seconds, nothing like this. But it's just a number that shows how heavy the query is. Now, what we can do is we can get multiple plans for one query, compare their costs, and choose the cheapest plan to execute. This way, SQL engine knows what to do to execute the queries as fast as possible. And we can also get those execution plans to understand how things work behind the scenes. So the database guardrails, they want to capture those signals, capture them from various applications, being HTTP code, being like your queuing mechanism, being your SQL database, capture all the details of like execution plan, indexes, metrics, and whatnot to finally prevent the bad code from reaching production. Because now what you can do is you can take your local environment, get the execution plan, compare this execution plan with what would happen in the production system, and immediately tell, hey, this query is going to be way too slow to be deployed to production, and you shouldn't do that. But it can also help you monitor the things, because now when we take a look at the monitoring of our database, we don't focus on your CPU spike to 100%. No, instead we tell you, hey, this query used to use an index a month ago, but it stopped using an index today. And this is because you deployed some changes. So now when the index is not being used, you can see table scan and the performance degradation. And this is something we can finally see and action upon. And finally, we can troubleshoot the stuff across the stages and make that much more readable, just because we understand this ecosystem and all the moving pieces together. So generally, we as developers, we need and we deserve to have these database guardrails. We can't wait for the issues to happen in production. We need to have those issues identified as early as possible. We need to push all those checks to the left to get them as early as it's possible, because load tests are slow, they are too late and are too expensive, and we just can't rely on them to find the performance issues. Issues need to be identified as early as possible. And being all of that said, I'd like to quickly run you through the solution we work on to show you how this can look in action. So in Metis, we basically build those database guardrails. So what we have is, once you register in Metis, you can get a project that shows you the recent activity, that shows you all the pull requests going through the system, and that can show you the actual developer-oriented dashboard. So for instance, for recent activity, you can see that, hey, your application exposes this REST endpoint, and this REST endpoint was called recently with some like post request, and it returned 201 HTTP code, okay? But when you go into that, you can see that, hey, behind the scenes, this is the SQL statement that has been executed. So you can see, hey, this is the SQL text, right? So we know what was going on, and we can analyze that stuff. We can immediately tell you, hey, this query extracted this many rows from this many tables, and unfortunately, it used table scan when accessing this table. So you can see this performance is critically low, and you should not deploy that to production. How do you fix that? Well, this is the impact you get, and this is how you remediate that. For instance, you can create an index like this one to improve the performance. So we can attach those things to your local environment and capture all those stuff just when you deploy application. Similarly, we can, for instance, analyze pull requests. For instance, we can take your pull request and tell you, hey, you wanted to run this schema migrations through your pipeline. But notice that, for instance, this schema migration is something that, hey, is basically risky. This is critical. This is some other issue. If exist wasn't checked and whatnot. So we can analyze those schemas before even executing them and tell you what's going on. But most importantly, when we prevent the code, we can also focus on observing what is inside the database. So we can show, for instance, charts like about infrastructure metrics and things that happen over there. But we can also show things about like the configuration of database. For instance, extensions that you have installed, or for instance, we can show other configurations like properties, showing you actual suggestions how to fix all of that. But when we focus on the database itself, we can give developer-friendly metrics and insights showing what's going on. For instance, we can tell actual things. This is how many transactions we have. This is cache hit ratio. Those are the indexes. And for instance, if we go to indexes, we can figure out that, hey, those are the indexes you have configured, but some of those indexes weren't used in like last 2 weeks. Maybe consider dropping them. right? Or maybe we would like to see the queries that are executed behind the scenes. So we can see that, hey, this is the query that is executed constantly in our database, and you can see how its performance changed over time, and maybe those are the insights about this query, that it uses table scan and should be fixed. So generally, we have a way to finally see what's going on behind the scenes, and generally make sure that we do not break the production. So Metis gives you the integration with source code, with your pull request, with your CI/CD, and brings you the true database observability, not raw metrics like your CPU spiked, but actual insights telling you this query is slow because it's ill-configured, and this is how you fix that. We integrate with various languages. We integrate with, for instance, GitHub Actions and other CI/CD providers. We provide this nice observability dashboard, and all of that together finally gives us this database guardrails. Because databases may break for so many reasons we saw during this talk. And we just can't wait for those issues to pop up in production. We can't wait for load tests to happen. We need to be proactive, we need to push to the left, and we need to have constant monitoring and observability. And with database guardrails and Metis specifically, you can finally get all of that and never go blind again. And being all of that said, I'd like to thank you for listening to this talk. And if you do have any questions, I'm happy to answer them now.
Hey, Adam. This was a great talk. Really enjoyed it. And you definitely reminded me a lot of my issues with databases, all about catching up with logging, which is, like you said, very distributed. Like you use queues, you use so many things, and it's just all over the place. It's a really good talk. I was wanting to ask you a few questions, if that's okay. So
let's go for it.
Yeah. Okay. So you said unit testing doesn't, testing in general doesn't catch performance issues. As one example, I totally agree. We kind of miss, catching a lot of the stuff that's not just very hardcore business logic. So all the security, the test, the performance, accessibility, those stuff get shoved a bit to the sides. Have you seen any patterns or best practices or just maybe awareness stuff that kind of works to give people more that mindset, also text those kind of cross-cutting concerns?
That is a very good question, actually. And I even have a separate talk, you can find it on YouTube, about testing in various domains, testing machine learning, testing UI applications, testing desktop applications, testing from the perspective of security. Generally, there is no simple solution because unfortunately, depending on what you develop, you need to have different approach to testing that stuff. For instance, let's just give one example. Let's say that you have machine learning pipeline that uses some ETL extract transform load to, prepare the data, then train your model, and finally put in production, right? Yep. Unit tests won't work for that, and integration tests won't work either. What you need to do in such a case is you basically need to run that pipeline for something like a golden input. So you you fix your randomness, you know what your input data is, you run it through the pipeline. Sure, you can watch some metrics along the way, but ultimately at the very end, you need to just check whether your model produces the proper output. So you need to try inferencing with it. And in that domain, there is no other solution. You basically need to run this pipeline end to end. And this applies, unfortunately, to other stuff. I mean, depending on your application, you may have some solutions that can help you, can aid a little bit this testing procedure, but there is no silver bullet that you would give you no answer in a second that, hey, all is good. And I recommend, taking a look at my other talk. And unfortunately, I also recommend, understanding what you do and just tuning the approach you have. Because even with security, we have the same thing. Depending on what security patterns we apply, then our testing procedure is going to be, way different depending on which mechanism we have or even in which country we run, right? Because the legislative is different in the case.
it was a good suggestions, and I think I remember. I mean, that was very helpful because I also remember, like you mentioned, you had this one slide talking about how adding a column, so like just changing the schema, would like cause so many changes in the database, like move things around back and forth. And I mean, you've even noted like potentially database outage, which I wasn't thinking about, like the stuff that it would actually require you to like save the data on the site temporarily, do some stuff, and like maybe you're out of memory, maybe you're out of space. So it's a lot of stuff to worry about with databases too, I guess.
Yeah, exactly. And the biggest problem here is like you won't capture that locally because your local database is small. And we learn only, and actually, sorry, I take that back. There is even a worse thing that is to it. The thing that once you start running this migration, you generally can't stop it in the middle. Because when you stop it in the middle, you need to roll things back. And this also time. So even if you realize, oh, something is not right, and I try to help that, then, well, you make things even worse. And predictability here is terrible. You don't know how long it's going to finish to complete, but even if you stop in the middle, then you can fix that in a minute, but you also need to wait minutes, hours until it goes back to a proper stable state.
100%. That's never, don't stop those things in the middle. That's only going to get worse.
Yeah, exactly.
Cool. Maybe my last question is, as your own personal developer preference, do you do query builders or ORMs, or do you just do like native SQL? Like, what do you do personally?
That's a very good question. That depends on the technology, actually. I mean, generally, ORMs are very hard when we apply extensions that give us like one tiny feature, and then you realize they are super hard to use. For instance, Hibernate in Java world is well known for things like when you start configuring like cascade delete or many-to-many relationships. They are often delivered like with some plugin into your ORM. And it works for some time, but then you realize, oh snap, it loses the data, right? So generally, I'm against using ORMs when you do not understand how they work behind the scenes and what you actually configured. And unfortunately, this is often the case. I mean, we copy-paste some configuration, right? Package JSON extensions and other stuff, or like annotations. We copy them from tutorials. Yeah, they seem to work in unit tests, but then things go wrong. So generally, if you do not really understand how your application is composed and how ORM deals with all the stuff which I mentioned, transaction isolation, caching, pooling, then in that case, I think query builders are much better. They are good enough. However, if you do know what's going on behind the scenes and you understand how it works, then ORMs are actually super cool. I mean, they make our lives easier. And once we tame their performance issues or configuration issues, they greatly speed up our development and makes our lives, much, much better in these terms. So the question generally is how much time you want to spend because you will always need to spend some time. Either spend the time on learning the stuff and avoiding the issues, or spend the time in debugging the incorrect configuration. So if you don't want to spend the time, stick with query builders, and that should be good enough. But then you just pay the toll on basically, constructing the queries, right? You always will need to spend some time somewhere.
I find query, I like that input because I know C# or .NET's like Link is probably like known to be a bit better maybe. It depends on the options. You don't always have like good ORM projects and stuff like that.
Just for people who may not be like very, very well known with .NET or familiar with .NET, Link in .NET is fantastic because you type strongly typed lambdas. This is cool. Many ORMs, for instance, in JavaScript or Python world, they are kind of stringly typed, right? So you need to use some different syntax or even put column or table names in like string literals. And this is terrible from maintenance perspective. In .NET, things are much easier just because you have strongly typed lambdas and you really use the same map functions or filter functions that you use with your regular arrays. So this is cool.
Yeah, it's a good point. All right, I think we'll wrap it up. There's like all the time we had. It's a great presentation. Definitely a great topic for developers. I enjoyed it a lot. So if you have any questions, anyone's listening, please drop them on the Discord server. We'll be watching that and getting those answered. Huge thank you to Adam. Thank you so much for being here and spending some time with us on this virtual session. It was great having you here. Also, thank you for the listeners who was on the call, and I hope you really enjoyed it. Keep an eye out for next session to be announced soon. In the meantime, if you enjoyed this session, remember you can always share that with your friends, communities, and peers. We have been DevSecOn, an all-inclusive community that educates and enables developers in application security. So thank you, and have a great day, everyone.
Thank you.